right, so what I'd like to look at today is something called the involute of a circle. Spelled this way. Here's the picture that sort of gives us a sense of what this thing is. You have a circle centered at the origin, and then you have the following. You have the radius of the circle, and you have a tangent coming out like this, and there's a point P over here, and the path we're interested in is that path. Now, that's not a very precise definition, so let me be a little bit more careful. There's sort of two ways to think about how we get this path P. One is you can sort of think about this red circle being like a reel, so to speak, and you're unwinding string off the side of it and pulling the string taut as you do that. So if you go to Wikipedia for a moment, there's a nice animation of that here. You can kind of see that over here on the, if you look at that, okay, you kind of see that animation. So let's watch that again, and you'll see it. There it is. Okay, and if you watch it carefully, what you'll notice is that the length of this tangent line is equal to the amount of arc that the point of tangency has traversed up from the x-axis. Let me sort of just demonstrate that. So what I'm saying to you is that this length here along the arc, there's a distance there. It's a section of the circumference of the circle. That distance is equal to the length of this tangent. So that fact will turn out to be pretty important. Our goal now will be to get a set of a parameterized function for the point P, x comma y. So I'd like two equations, x of t equals y of t equals, that would tell me P's position, or the point P, for any value of t. Okay, so we're going to start labeling some things and go from there. So we're going to let t be this angle, the angle from the x-axis to the radius of the circle. We're going to denote the radius of the circle to be r. And this is another good example of a problem where if you're going to try and create the parameterization, you're probably better off considering two vectors, and then we could just add them component-wise to get the parameterization we want. So that starts off quite easily if you decide to do it that way. If we look at the vector we really want is the vector OP, that one. There it is. We'll just draw it out like that. But what do we know? We know that OP, that vector, is just the sum of OT plus TP. Okay, so let's just work on one vector at a time. We'll add them together, and then we'll have the equation we want. Alrighty, so if we just want to look at OT, we're interested in the location of this point, so to speak. If we can find that, and we sort of know what this vector is. Well, this is just a circle, and we know the parameterization there would have to be this. So OT would have to equal r cosine t times I plus r sine t times j. Now, why is that? If for some reason you're doubting and you're not quite remembering why, just drop a perpendicular from there, and then you need to ask yourself about the two components. Here's your x component, here's your y component of this vector. Or you could think of the x component as moving in the I direction, where I is this vector, and y is moving in the j direction, where j is this vector. Okay, so t is the angle that's right in here, and then you just have some right triangle trigonometry. For example, if you did the cosine of t, that would be x over r, and there you get r cosine t. And the same reasoning, you do sine of t equals y over r. And then that yields this one, just like this yields that one. All right, so we have the vector OT. Now what we'd like to do is get the vector TP. And to do that, what I'm going to do is I'm going to sort of look at this piece of the curve here and sort of expand it. Like we're going to zoom in on that, so to speak. All right, so what does that look like? Here's our axes again. Here's our circle. Okay. We've got the vector OT coming up. There's the point T. And then out to P over here. Okay. So we have to have a couple of realizations. First off, we discussed that the length along the arc that's been traversed here is equal to the length of vector TP. So maybe we should sort out that first, get a sense of how long TP is. All right? And that requires that we remember something about angles drawn or described in radians. So we learned a while ago in some kind of geometry class, maybe in high school, but that the angle in radians, theta, is always equal to the arc length divided by the radius. And so this arc here, the arc from this point up to this point, right? We'll call that S just for a moment. And that's the same thing as this S up here. Well, what do we know? We know theta is T. We know the radius is just R. So that implies that S, the arc length we're interested in, is equal to T times R. So now we know a length, at least, of TP. We can say that the vector TP has length TR, where T is our parameter. Okay. The second thing we're going to need to do is we're going to need to sort of figure out how we can describe the components of vector TP using the parameter T. Because we're using the parameter T in the other vector that we wrote up here. So this new vector, I'd also like to have a T in it. So my whole thing when I'm done is just a function of T. All right, so to do this, I'm going to draw a second x and y axis. And then hopefully have some realization. So here's the second x and y axis, just to sort of give us some reference. If we think about it, this angle's T here, so is this one. That has to be T. And the reason that's T is because they're alternate interior angles. Okay? Where OT here, this vector, is acting like the transversal to these two parallel axes. Those two x-axes, we'll say in quotes. Okay. Then that tells us something else, actually. Then we know that in here, that angle has to be pi over 2 minus t, because there's a right angle between these two axes here. So that's a right angle right there. And then we also know that vector TP and vector OT are perpendicular, because a tangent to a circle is always perpendicular to the radius at the point of tangency, which means that this angle over here now is also t, right? Because this angle on the left of the vertical y-axis is pi over 2 minus t. So if I do pi over 2 minus t, I get just t. All right, well, that's really promising now, because now what we can do is we can look in here, and we have another right triangle. Okay, here's our x component of that right triangle. Here's the y component of that right triangle, and we're ready to go. So we can say the vector TP would equal, if we're looking for the x-coordinate, t is up here, there's the angle t, we would have the sine of t equals opposite over the hypotenuse. The hypotenuse's length, as we discussed earlier, was tr. So that's what we get there. So that implies that x equals t times r times the sine of t. Okay. We should also make a note here, this is moving in the positive x direction. This vector generally moves to the right, so it makes sense that that component would be positive. Okay. And then y would equal, well, we'd use the same kind of reasoning. We'd end up with cosine of t, however, because the side y in this little red triangle is adjacent to the angle, would equal y over tr, or rt. And then we have the following. We have y equals tr cosine t. But with one small thing we need to be careful about, we're moving in the negative direction, so there needs to be a negative here. Now you have it. Now you have vector Tp. Tp is the vector tr sine of t times I plus tr, or I should say minus actually, minus tr cosine t j. So finally, we can write the vector we're really interested in. The vector OP is going to be the sum of those two vectors. So we'd add the two x components. So it would be r cosine t plus tr sine t times I. And then we're going to have plus r sine of t minus tr cosine t j. And that's your parameterization for the involute of the circle.